Got it? Okay. Let's begin with a word of prayer. Dear Heavenly Father, we thank you again for this opportunity we just have to meet together and talk about you openly. Thank you, Lord, for your creation, that we can understand it, just a little bit of it at least. And I just pray that you'd help us to understand the math we cover today. I just help you, Lord, just pray, Lord, that you be glorified, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so let me just take 1 second more to talk about the area function. So here's a foreshadowing example. So what would the area function be if I look at y equals x, right? What's the area under the y equals x function if I say go all the way out to from 0 to t? Like I go from 0 all the way out here to x equals to t. What's the area at x when x is equal to t under the line y equals x? 1/2 base times height, right? What's the base? T. What's the height? Also t, right? Y equals x. So the area is 1/2 t squared, right? So what's the derivative of the area with respect to time? Well, with respect to t, it's 1/2 times 2t, right? It's t. Or if you like, a prime of x is just equal to x again. This illustrates the thing I was telling you last time, that the derivative of the area function is just the function for which we're finding the area of. So antidifferentiation has this connection with the problem of finding areas. And again, we will explore this more fully after the next test. So with this little motivational comment made, let's get back to the main order of business, which is calculating antiderivatives. So what did we do? Last time we looked at our main examples. Our basic antiderivatives were what? Or basic indefinite integrals, right? Indefinite integrals. Indefinite integral, if I ask you to calculate the indefinite integral, we must add a constant, all right? So let's see here. Basic examples. Integral of x to the n dx was x to the n plus 1 divided by n plus 1 plus a constant, right? Now that's for n not equal to 1, minus 1 rather, right? What happens if n equals minus 1? We have integral of 1 over x dx. What's that equal to? We talked about this last time, natural log of x plus a constant. Now I'm assuming that x is greater than 0 for the moment, all right? What else do we do? Integral of e to the x dx was what? E to the x plus a constant, right? Those are your basic examples. I would love to throw sine and cosine in here, but we already cut out that part of our brain earlier in the course. Don't be sad, be glad. Fine. Now, of course, example number 1 here is many-faceted, right? I mean, if we integrate the square root of x dx, what's that actually look like? So we do, x to the 3/2 divided by 3/2 plus a constant, right? But I like to write that as 2/3 x to the 3/2 plus a constant, right? Or here's another one. What about dx over the square root of x? X to the minus 1/2, right? So that's what? That's x to the, what's minus 1/2 plus 1? Yeah, 1/2 again. Division by 1/2 is the same as multiplication by 2. Or if you want me to rewrite it, it's 2 square root of x plus a constant, right? So these are our basic, we need to know these almost without thinking, right? I mean, you want to have these ingrained for the test and for the remainder of the course and so forth. Now, there's another class of examples that you could also do. Examples where you're just given something, basically true-false questions, true or false. The integral of x e to the x dx is equal to e to the x. It's equal to x e to the x minus e to the x plus a constant. True or false? How do you check something like this? What does it mean for something to be the antiderivative or the indefinite integral? We need to check that the derivative of the claimed indefinite integral here, so d dx of x e to the x minus e to the x plus a constant. For this to actually be true, what do we need this to work out to? What's that? X e to the x, exactly. So what do? We do product rule, right? So we get e to the x plus x e to the x from the first term, right? Because we have derivative of x is just 1 times e to the x plus x times the derivative of e to the x, which is e to the x, then minus e to the x plus 0. What happens? These guys cancel, and we're just left with x e to the x, which is precisely what we want. You're like, but there's no dx. That's right, there's no dx. We're not looking for dx in the answer. We're looking for the thing which is being integrated, the so-called integrand, which is just x e to the x. That dx there is just a notation. You should think of dx as being paired with the integration sign. It's telling us we're integrating this function with respect to the x variable. All right? I should not write an integral without the dx. If you don't write the dx, it's technically wrong. And it'll get you into trouble. Not writing the dx will make you make mistakes in what follows. It's very important not just to write, like, you have not seen me. At no point did I write this, right? This is lazy. This is wrong for this course. Okay. Now, so what I'm tell you, I shouldn't even write this, right? I mean, this, Now, would I take off all the credit? Of course not, but I'm just trying to help you. Do not skip the dx. It's important. Let me show you why. I mean, it's just a notation, but it's a helpful notation, all right? So the next topic is that of U substitution. So here we learn how to calculate some antiderivatives which are a little bit more complicated. So I'll show you how this works. Suppose you wanted to integrate x times e to the x squared dx. Probably somebody here can guess the answer. Can anybody guess without writing stuff? What if you used e to the x squared? When you differentiate e to the x squared, what happens? You get 2x times e to the x squared. So if I divide that by 2, that'll work. But we'd rather not do math in our head, right? We'd like to write down work and kind of have some kind of systematic way of doing it. So here's what we do. When you see something like this, it's not on our list of basic integrals, right? It's not one of these three things. So what do we have to do? The only other choice at this point in our arsenal is what's known as u substitution. What we're going to do is make a new variable, u, and try to make a substitution so that it looks back, it ends up looking like these. But instead of these, actually, it's going to look like this. It's going to look like the integral of u to the n du is u to the n plus 1 over n plus 1, or it might look like the integral of du over u is the natural log of u plus a constant, or it might look like the integral of e to the u du is equal to e to the u plus a constant. So actually this, one of these three guys, is going to be our target. We want to make a substitution so that this looks like one of those, maybe with a number or something, multiplying it. So with that goal in mind, you got three choices, right? What substitution are we going to make here? U equals to what? What's that? X squared. Very good. Now you guys remember we took the differential before? We're going to do that again. What's the differential of u? It's du is what? 2x dx, right? There's that differential we talked about earlier in the course. It's come back again. And so this informs my substitution. So what do? I've got integral of x e to the u dx, right? I'm not done yet, right? In fact, the substitution is not successful until I have eliminated all the x's. So some people wouldn't even write this down. Some people would say the step I just wrote is wrong. I just say it's a transitional step, okay? I won't deny you this step if you want to use it. How can I get rid of the x? There's a couple different ways you can do it. The one way you can do, and this pretty much works every time, is you can solve this for dx, right? dx is equal to what? dx is equal to du divided by 2x. Very good. So I can go in here. I've got x. That's there. E to the u. My dx is actually du over 2x. Now, this was a successful u substitution because the x's cancel. See what we're left with? 1/2 integral of e to the u du. But hey, that's one of our basic indefinite integrals, just written in the u variable instead of the x variable. So now I can go back and go, oh, aha, well, that's e to the u, 1/2 e to the u plus a constant. And then the finishing blow, put u back to x squared. Oh, I'm sorry, it was too violent. Let's see here, 1/2 e to the x squared plus a constant. And again, you can play the true-false game. Did that work? You can differentiate that, right? If you differentiate it, you get back to x e to the x squared. We win, right? No? All right. Your excitement is contagious. Let's see here. Properties of integration, we have basically two to work with. One is that f plus g dx is equal to integral of f dx plus integral of g dx. That's one thing we got. The other thing is that we can pull numbers out. So those are properties we got to work with. Es bueno? All right. Let's look at another.
So basically you just took out x over 2x and x.
Right, right. Now there is another way you could have done it. Instead of solving for dx, you could just as well solve for x dx equals to what? Right, so you could make the substitution like that too, and just substitute in x dx rather than dx. The substitution, the way it's actually implemented, there's a few different ways to look at the algebra. Honestly, I personally usually look at x dx rather than substituting in dx because it's less work. It's okay. Was it a question?
I was just asking how we got d was equal to 2x dx.
Oh, we took the differential. So like generically speaking, if u is equal to f of x, more generally, then du will be f prime of x dx, which you could write as df dx dx. So it almost seems tautological if you set u equal to f. Let's see here, another example. How about this? Integral of x plus 3 times the square root of x squared plus 6x. Yeah. Sorry, I have to be very careful. It's very easy to make up integration examples which can't be done. So I have to be careful. All right, so this example, what are we going to do? Well, looks like it's going to be one of these guys, right? I'm guessing we're aiming for like square root of u. So typically, something like this, you just look at it and go, well, I got some choices, but you make a choice and you try to run with it. If it doesn't work, you try something else. So our first choice is going to be the right one. I'm gonna do u equals to x squared plus 6x. So sorry, I've poor planning on my part. I'm going to put the equals down here. So we've integral so this will be square root of u, right? Now what's dx? Well, what's du? 2x plus 6 times dx, right? In other words, du is twice x plus 3 times dx. I'll solve for dx for the moment, because more students get that. Not my favorite, but it's just, for some reason, what I did in red over there, it troubles some people. So I'll behave and solve for dx. Solve for dx. Plug it in. We get du over 2 times x plus 3. If this was a good u substitution, the x's will go away. Did they go away? Indeed they do. The x plus 3 cancels, right? You're left with 1/2 the integral of the square root of u du. Which is what? 1/2 of 2/3 u to the 3/2 plus a constant. That's a basic indefinite integral, right? One of the power rules. We did that in x. I had it here and I erased it. It was about the same place on the board earlier today. You guys can ask questions. It's fine. We got time. Yeah. Oh, not yet. Not yet. I mean, let me get this out of our system. A few more examples, then I will take homework questions. Yes, of course. Yes, sir.
How do you know it was u in the equation? Like, how do you know what u was?
That's the most difficult question to ask. How do you know what to make u? The answer is practice. Ooh, it may not even be possible for a general integration. So kind of, but as a rule of thumb, what you do is you look at it and you kind of just pick the meanest, baddest looking thing and make it u. Right? It's kind of like a street fight. Pick on the biggest one first. If you can take him down, then the rest of them will run away. I don't know, there's different philosophies. Maybe you should pick on the smallest one and take out an eye or something. I don't know. Various philosophies exist. Yes?
You would want us to plug u back in?
Oh, we're not done. Yeah, thank you. Sorry, I got distracted. So the 2's cancel. And 1/3. You know I'm easily distracted here. 1/3 u is x squared plus 6x quantity to the 3/2 plus a constant, and there you go. You start to see the power of the method, right? Like if I just asked you guys, tell me some function that if you differentiate it, you'll get back to x plus 3 times the quantity square root of x squared plus 6x. There aren't so many people who can just spit back at me, I'll just take 1/3 of the quantity x squared plus 6x to the 3/2 power. Duh. Right? No, but this gives us a clear path to finding it. It's really kind of an amazing little trick. But yeah.
Where did 2/3 come from?
The 2/3 come from the n equals to 1/2. So if I have 1/2 for the, like u to the 1/2, 1/2 plus 1 is 3/2. So I get 3/2 divided by 3/2. But division by 3/2 is the same as multiplication by 2/3. So yeah, very good question. Are we good on this example? Should I do another? Let me do another. So I hope you're starting to see the algorithm here. What's the algorithm? You face an indefinite integral, right? First of all, you choose a possible u substitution. You say u equals whatever. You calculate the differential du. You solve for dx. Then you plug in dx and you plug in the substitution into the problem. Hopefully the x's cancel, you integrate, and then change back to x. And that's what we do. So again, the process, step 1, choose a u equals to blah. Step 2, calculate du is equal to d blah dx times dx. Solve for dx equals to du over d blah dx. 3, plug du and u into original integral. 4, integrate. With respect to u, step 5, convert back to x. Let me try out this 5-step program on this example here. Integral of x to the 8th divided by the square root of x to the 9th minus 6 dx. This is an awful lot like number 2 on your homework for what it's worth. All right. So step number 1, I got to choose u equal to blah. What should u equal to? X to the 9th minus 6. I think we have a winner. What's du then? Du is 9x to the 8th dx. So there's step number 2. We solve for dx, right? Du over 9x to the 8th. Okay, now I can plug those in. I've got x to the 8th over the square root of u. dx was what? It was du over 9x to the 8th. We have a winner. The substitution worked, right? What are we left with? 1/9 integral of u to the minus 1/2 du. Which again is one of our 3 basic indefinite integrals, since we don't have sine and cosine or cosh and sinh to work with in here. So sad. Hey, I could do cosh and sinh. We have exponentials. No. Man, you guys are no fun. There's so much calculus I'm not showing you. It seems wrong. You should demand a refund. 1/9 u to the what? Minus 1/2 plus 1 is, oh yeah. U to the 1/2 divided by 1/2 plus a constant. So that is 2/9. And my u is what? X to the square root of x to the 9th minus 6. Close the square root plus a constant. There you go. Es good? Es bueno? Let me take a gander at your homework here for a second. Yeah, I got a couple more to do, and then we'll switch over to your homework questions, okay? I'll make sure I give you a good cross-section of examples here before we go back to other homeworks, okay? Because this is pretty much it for the next test, right? We have the differential calculus we did before. What's that? What? Did I say something? Was it something I said? Next, oh, why is there? You don't like tests? Oh. Yeah, there's only one more. Yeah, test 3, and then the final. I know, right? Time flies when you're having fun. Let's see here. How about this? How about the integral of e to the 3x, or let's say minus 3x, plus x cubed, and let's say 4x cubed, e to the x to the 4th dx. How should we attack a problem like this? We shouldn't? No, we should. We should. We definitely should. We break it into 2 pieces, all right? So this is e to the minus 3x dx plus the integral of e to the x to the 4th times 4x cubed dx. I wrote the 4x cubed second rather than first because I wanted to be different. You hope you can forgive me for doing that. I'm just going to use a slightly different formatting on this example. So for the first integral, I should say, we're going to let u equal to what? Negative 3x. So du is equal to minus 3 dx, right? So dx is equal to minus du over 3. So just to get that out of my system, that's going to give us the integral of e to the u times minus du over 3, right? Now, we have another integral to deal with, right? So obviously, it's the second u, so we'll call this one w. Okay, w equals to what? X to the 4th, yes. And then dw is what? 4x cubed dx. Was it? Our third dw? Is that a thing?
That was his sister's name on the show when we were like 11.
Ah. See, People say this stuff about you should like study Shakespeare so you can understand your common men. Nonsense. You should watch lots and lots of children's programming. That's the way to. Yeah. So. Anyway, okay, so you see that, in fact, that 4x cubed dx was really just what? It's really just dw. And we have the integral of e to the w dw. So now we can integrate both of those. We get minus 1/3 e to the u plus e to the w plus a constant. And then finally, bring it back to x's, right? So that's minus 1/3 e to the minus 3x plus e to the x to the 4th plus a constant. Yep.
Why didn't you do for the dw? Why didn't you do dx equals dw over 4x cubed?
You could do that, and then the 4x cubes would cancel.
Oh,
It's just, I mean, I don't want to be a slave to that method, let's say. I could also just look and say, aha, well, I've got that,
okay.
but that is this. So I can trade it for a dw. But, yeah, you can also solve for dx if you want, right? I just get bored with solving for dx after a while. I shouldn't get bored with it. I should just keep doing it for you guys. I'm sorry. I'm a bad math professor. You should send me to the corner or something. Let's see here. All right, so. I need an example, another example. How about this one? Integral of x times the square root of x plus 3 dx. This gets a lot of people in the Math 131 class, so, the other calculus, the 5-day-a-week calculus, right? When I put this on a test, I invariably get about half the class. They get it wrong a lot of times, which is unfortunate because this is just, it's a little bit different, but it's just a u substitution again. So what do we make u? We make this the u, right? So du is actually equal to dx in this case. So we've got x square root of u du. But there's an x. What do I do with the x? What is x in terms of u? If x is equal, if u is equal to x plus 3, then what's x equal to? Yeah? Indeed. See, that wasn't too painful, right? And so to get rid of this x, I just make a substitution of u minus 3. Now, admittedly, the algebraic pattern here is different than all the other examples I've done today, but logically speaking, it's really not so far removed from our previous examples. So we've got u minus 3 square root of u du. Now what to do? Now we do algebra. See what this is? This is the integral of what? What's u times the square root of u? Tell you what, I'll do one more step. U square root of u minus 3 square root of u du, which is the integral of u to the 3/2 minus 3 u to the 1/2 du. Now I can use linearity of the integral to integrate each term separately. Use the power rule as usual. What's 3/2 plus 1? 5/2. divide by 5/2 is the same as multiplying by 2/5, right? So this is 2/5 u to the 5/2 minus 3 times 2/3 u to the 3/2 plus a constant. And of course now, step 5, I got to put it back in terms of x, right? So this is equal to 2/5 x plus 3 to the 5/2 minus 2 times quantity x plus 3 to the 3/2 plus a constant. Again, the question John asked me earlier is still the most difficult question, really. What do you make u, right? But my answer to that really is just choose something and try to work it out. If it fails, try something else. We haven't tried something and failed yet. Like I have just chose the right u for you in each one of these examples. Let's do an example where making the wrong choice of u doesn't work. All right. So example, let's try to integrate, I don't know, e to the x over 3 plus e to the x dx. I argue, as I look at that expression, there are kind of like two things I would think about making a u equal to. What are the two things that kind of pop out at you as possible choices for u?
3 plus u x.
Right. Or how about just e to the x, right? Those are kind of the things I would think about doing. So actually, you could go either way. Actually, either choice will lead us to something that's good. So let me choose the bad choice to start with. This is kind of a I'm going to work this example two ways, and you can decide why we should do it one way or versus the other. If we choose u equal to e to the x, then we get du is what? E to the x dx, right? So with respect to that substitution, we have, upstairs we've got a du, downstairs we got a what? Three plus u. You're like, well, oh man, that's not on my list of basic indefinite integrals, right? But you could do this. You could be like, well, I'll make another substitution beyond this one. Right? So just step 2, let w equal to what? How about 3 plus u? If w equals 3 plus u, then dw is equal to du. So I can, with that substitution, get this to the integral of dw over w. And then we're golden. Right? Because now we're back to a basic indefinite integral. So the answer is what? Natural log of w plus a constant. But now I have to undo my substitutions, which is what? The natural log of 3 plus u, which is, of course, the natural log of 3 plus e to the x plus a constant. So that choice of u wasn't wrong, it was just suboptimal. If we made the other choice, the one the gentleman in the back said to start with, we would have had less work to do. Let's see how that, anybody have questions about this, or can I? Okay. So, same example, different substitution. If I let u equal to 3 plus e to the x, right, then I have du is e to the x dx. And so my initial substitution immediately takes me to, to du over u, which is pretty nice because that's like 3 steps, right? Natural log of u plus a constant, which is the natural log of 3 plus e to the x plus a constant. So you see, we get to the same answer, but with a shorter process, right? So, yeah. Goes back to our basic, one of our basic antiderivatives, the derivative of the natural log. I mean, so this is like tied with the other identity, which is that the derivative with respect to x of the natural log of x is 1 over x. So if we integrate 1 over x, we need natural log. And I'm assuming x is positive every time I say that for now. Okay, yeah.
For the IQ way they did it, for the GW over W, I don't know why, like, the first red to the first purple, I don't understand that.
From the red to purple?
Yeah.
Well, I have here that du and dw are the same, right?
Why would we even bother calling it W? Or like, if they're the same thing, why don't we just...
Well, they're not the same thing. W is 3 plus u.
Oh, okay.
Now, maybe in this other one I could say u bar, u bar, u bar. It's not the same u, right?
Okay.
All right, I think I've shown you enough u substitutions for now. We can come back and do another half dozen of these some other day. You need to get totally bored with these in the good way. Like, I'm bored of this. I already know how to do this. Like, enough already. I've got chemistry to study. Whatever it is that you're studying. I don't know, biology, anatomy, whatever it is you guys study. Fantasy football stats, I don't know. I haven't lived your life. I don't know how to walk a mile in your shoes. I don't know all that. Is that something we say? I don't know. Yes, please do. That was my rather complicated way of saying go ahead and ask homework questions. Uh-huh.
I remember we went over this, I think probably even 2 times, because I think some of us...
Yeah, 3's a charm, no problem. So homework 10, which problem?
10.
10.
I did it right, I did it the way that you showed us. I just had different numbers.
Is that the soup can one?
It was the soup can one. But whenever I put it in, it just doesn't, I don't get it correct.
Yeah. You're doing it. We have done that one twice before. Yeah, I don't really want to write that one out again. But what I will do, since you asked me, is look at yours. Oh. Well, what answers were you? Just a second here. What was your last name?
Butler.
Say again?
Butler.
Ah, okay. And that was homework 10, right?
Yeah.
I'll get there in a second. Look at all these green checks. It's all green. Until number 10, right? Let's see here. Number 10. So you said you worked out the 3.53 and 0.72?
Yeah.
Okay, so let's see here. The capacity is 28 inches cubed, and we're supposed to do what again? It's right circular cylinder, find the radius and height of a container that has a capacity of 28 cubic inches, and constructed with the least amount of material. All right, so So let's see here, same song and dance. Volume was pi r squared h, and we have 20. Oh, the capacity. We need to have a capacity of 28 inches cubed. Okay. So we're given that the volume, that this is equal to 28 inches cubed, right? And we want to minimize the surface area of the can, which would be pi r squared plus pi r squared plus 2 pi RH, because that's the area of the top, area of the bottom, area of the sides. Let's see here. Let's say H is equal to 28 over pi r squared. And so the surface area is equal to 2 pi r squared plus 2 pi RH, but H was 28 over pi r squared. I'm going to set r equals to x just to make calculus be friendlier for us. So surface area is 2 pi x squared plus, what we got here? 56 over x squared, right? So if I differentiate with respect to x, that should give me the critical radius. So the derivative of the surface area with respect to x gives me 4 pi x minus 56 times 2, times minus 2, well, times 2, yeah, divided by x cubed. Set that equal to 0. That gives me what? That gives me 4 pi x is equal to, what's 2 times 56? 112? 112 over x cubed, yeah? Because of the minus 2 power here, so power rule gives me minus 2.
Oh.
Is that it? Yes, we found it. But we'll finish this. Okay, so that gives us x to the 4th is equal to 112 over 4 pi, right? So therefore, x is equal to the 4th root of 112 over 4 pi, whatever that is. Don't happen to know that one off the top of my head for some reason. But it's okay, this calculator is not evil. It will tell us the answer. 112 divided by parentheses 4 times pi. 4th root of that thing. All right. Yeah. No. Did you guys get 1.728? Did you guys get that? Or that's what I got. That is not, well. Just a second, let me try my numbers again. Well, that ain't cool. Hey, 1.73. The answer key's got 1.65. Am I missing something here? Have I done anything different than we did before? For x? You got 3.6?
Yeah, for column.
You have 3 points. How did you get 3.6?
Because don't you take the 4 from square root of square root of 112 over 4 pi?
So 100, well, what's that?
So I did just that, and
So 112 divided by 4 pi, I get 8.91 something or other, right? So if I take 8.9 and then I take the square root of that, excuse me, square root of 8. I'm trying to see if they've got a round off error thing. I cannot get their answer. Yes.
Right after you have the step for your finding your equation for surface area, you cancel out the r's, and shouldn't it go to just one r on the bottom instead of having to be
Oh, thank you. So you're right here, right?
Yeah.
Should just be x. Oh, okay. I knew this. I thought I had a cube root before. I did, right? Over here I should get a cube root. If that changes to x, this changes to x squared. The 2 goes away, right?
Yep.
Thank you.
You're welcome.
Hey, I did it right 2 times before. There's about a 60% chance I'll work this right. 66. Yeah, whatever. Oh, wait. So that's x cubed is 56 divided by 4 pi. And so that is 56 divided by 4 pi. And I want a cube root. And I am really hoping that works out to 1.65. Find out soon. Yes, 1.65. There we go. And that's the answer for your problem, Ms. Butler. And then the height works out to about 3.29 when you plug it back into the other thing, okay?
I don't know why, but I got 4.4.
From the cube root of 56 divided by 4 pi?
Oh, it's 56.
Yeah, because there was no 2, so when we differentiate, we just get minus 1, x to the minus 2, like that.
And now I keep getting 3.52. I'm comparing the answers that I got.
56 divided by 4 pi is what? No. It's like 56 divided by 12, give or take. So it should be around 4 point something or other.
Make sure you put 4 pi in parentheses. And it'll go order home over.
Yes, 4 pi in parentheses is good advice. Do.
Okay, now,
Yes, sir.
can you just take a moment to explain kind of how the natural law of finance or that, how that kind of works? I can do it, like I can see how it's done, and I can redo it, but you just kind of explain the logic behind it.
The derivatives of natural logs? Yeah.
So like, we're taking the derivative of the natural log of like 8x squared times 5x.
Derivative of the natural log of stuff. So the basic result is that the derivative with respect to x of the natural log of x is equal to 1 over x. I'm assuming you don't want me to work that back out again. I mean, we could, but we worked that out. That follows from implicit differentiation of the exponential. But if you accept that as being a given, then the chain rule says this. d dx of the natural log of u is equal to 1 over u times du dx, right? But how I actually usually use this formula is as follows. For example, if I'm going to differentiate the natural log of 3x plus x cubed, what I do is I just differentiate the inside, which is going to give me 3 plus 3x squared, and then I divide by the argument. Or if I was differentiating, here I'll use a different letter, ddt of the natural log of 3t plus 7. So I do 3, because that's the derivative of the inside function, divided by 3t plus 7. Make sense? Now, what you might be asking me about actually is the larger program of logarithmic differentiation, right? Which is kind of a different animal altogether. Suppose you've got y is equal to, e to the x times the square root of x plus 3 divided by x cubed plus x squared plus x, for example. Calculate dy dx. Then what you do is you go, okay, well, this tells me the natural log of y is equal to x plus 1/2 the natural log of x plus 3 minus the natural log of x cubed plus x squared plus x. There, I have used properties of logarithms. In fact, pretty much all of them. We use that the natural log of a product and divide by c would be like natural log of a plus the natural log of b minus the natural log of c. That's one of the things I did for the larger pattern. Now, a I'm thinking of as e to the x. The natural log of e to the x is just x again. That's why I have that x there. Also, the natural log of the square root of x plus 3, well, hey, that's the natural log of x plus 3 to the 1/2. And so by then we can pull the half out. So that's where that came from. Now that I've done that, I can differentiate both sides implicitly. On the one side, by the chain rule, I get 1 over y dy dx. dy dx is actually what I'm